So the last video of the chapter is section 11.5. And it's the last of our conic sections, which is going to be hyperbolas. So here's our conic section video, and what we're going to do now is we're going to slice our conic, our double cone, with a plane, but now we're going to do it, this one's going to do it parallel to the vertical axis. And we'll see that it's going to slice a piece off of both the top cone and the bottom cone. And once those fall away and it turns to face us, we'll see the cross section that's left, and we'll see the two branches of our hyperbola. So that's how this thing is manufactured from a conic. We'll take a look in just a moment at first the definition of a hyperbola, and then we'll take a look at how we construct it from the definition. So there's our blue hyperbola with the two branches opposite each other. Okay, the definition of a hyperbola is the locus, which again basically means collection of points in a plane such that the difference of the distances from two fixed points to any point on the hyperbola is a constant. So with ellipses, it was the sum that was the same. It was the length of that string that we talked about yesterday. Now it's the difference between the two distances. So distance 1 minus distance 2, if distance 1 is bigger, or distance 2 minus distance 1, if that's the bigger one, is always going to remain the same value. They're always going to be the same distance apart from each other, or difference in length. So we have a point here, we have a point here, and so the idea is that we're going to find all the places where this is distance 1 and this is distance 2. We're going to find all the places in the plane such that the difference in those two lengths is always going to remain a fixed value. And so if we take a look at that as constructed, here are my two foci, because the two fixed points are again going to be our foci, just as they were with our ellipses. And so what happens is, as I drag this control point around, it's adjusting distance 1 and distance 2. Distance 1 is the difference, or the length, of this segment between D1 and the control point. Distance 2 is the length of this segment between D2 and the control point. Notice as I move it in here, distance 1, distance 2, and the absolute value of their difference. We do the absolute value just so we can ignore any negative effect. We just care about the length. All three of these are going to change values. Notice I'm also not getting the graph of my hyperbola right now because this is not staying a constant. But as soon as I drag this out farther, now what happens is, even though distance 1 and distance 2, this distance and this distance are changing, this is what I basically had drawn just a moment ago, notice that the difference of the two distances is remaining fixed at 4.24. So there's one branch on my hyperbola, and if I drag it to the other side, now I get the other branch. Again, notice that the foci are on the inside of the curves. And the way that we adjust the shape of our hyperbola is we either adjust that difference length, or we can adjust the foci relative to one another. So if I want, for example, to drag this focus out here more, it's going to give me a wider hyperbola. It's also moving my center. Do you see that? If I drag the focus closer, now I I get a skinnier hyperbola. Again, it's shifted my center a bit. So that's the idea. And what's really going on here, just so you can see, is again, just like for ellipses, we have two circles. While I'm dragging this around in here, notice the two circles do not intersect. But as soon as I go out here, now what happens is as soon as the circles start to intersect each other, now all of a sudden we're finding that locus of points and getting our hyperbola. The difference, again, once I'm out here, is always remaining the same because the difference is going to be the length between D1 and D2. So that's the idea of what's going on. Okay, let's take a look at some terminology. When we have our two foci, call this focus 1, we'll call this focus 2, and we have our hyperbola, we have our center, that's going to be h comma k like it's been for all the other conic sections. The distance from the center to a focus is again going to be c, just as we saw with our ellipses. We have vertices on hyperbolas, and the vertices are where each of the branches starts, and they will be in line with the foci. I didn't draw it perfectly here, but we'll see it better in just a few minutes here. These are the vertices. This is vertex number 1, vertex number 2. The distance from the center to a vertex is our A. We also have a B, which we can't really see exactly in this picture, but I'll show it to you in a few minutes here when we actually draw a graph. B is actually the distance going in the opposite direction. And what A and B are going to combine to give us is what I call a guide box. So we'll see that as soon as we go to actually draw a real one. But A, B, and C all come into play here again, just like they did with ellipses. Now, the important thing to understand is there are a lot of similarities between hyperbolas and ellipses. What you want to stay focused on, though, are the differences. If you stay focused on the similarities, you'll get them confused. If you stay focused on the differences, you won't have as big an issue. All right. Let's take a look at the equations. So for hyperbolas, and again, our center is going to be at h comma k. We have hyperbolas that open horizontally in the x direction. We have hyperbolas that open vertically in the y direction. The ones that open in the x direction, the equation is x minus h squared over a squared minus y minus k squared over b squared equals 1. Notice it's the same as our horizontally stretched ellipses. The only difference is we have a minus here instead of a plus. Likewise here, it's going to be y minus k squared over a squared minus x minus h squared over b squared equals 1. Notice this is a bit different. On ellipses, a squared and b squared switch places. On hyperbolas, it's the y minus k and x minus h squared, parentheses, that switch places. The difference here is the fact that on ellipses, a squared was always bigger than b squared. Now, a squared is not necessarily bigger than b squared. Not necessarily. Sometimes it's bigger, sometimes it's smaller. Sometimes they're both the same, which does not happen with ellipses, because then it becomes a circle. So let's take a look at an actual example and work through it, and I'll show you everything that you need to know. So we have, for example, x minus 2 squared over 4 minus y plus 3 squared over 16 is equal to 1. Notice that this is one of these hyperbolas. It's going to open in the x direction. The way we know which direction it opens is whichever letter comes first on the top, that's the way it's going to open. Now, that's assuming you have it in standard form, where this is the positive fraction and this is the negative fraction. I call this negative because it's preceded by a minus sign. Okay, so if you write it in this form, the first one, that letter on top tells you which way it's going to open. Likewise, the first one, the letter on top tells you which way it's going to open. So this is going to open in the x direction, so it's going to open this way. Our a squared is 4, and our b squared is 16. Even though b squared is bigger than a squared, that's okay on hyperbolas. It's one of those big differences. So a is equal to 2, and because the 4 that it came from was under x, that's in the x direction. B is equal to 4. That's going to be in the y direction because the 16 was underneath the y. So let me get a graph grid here, and we will start to put this thing on a graph. Okay. So our center here, we know is h comma k. That's going to be 2 comma negative 3. Again, be careful, just like with parabolas. You've got to go to the x parentheses first, either here or here, to get your x coordinate, and then you go to the y parentheses to get your y coordinate. Otherwise, you'll have those reversed. 2, negative 3 is our center. I put a little x. We're going to go 2 units each way in the x direction. So to the right 2, to the left 2. We're going to go 4 units each way in the y direction. 1, 2, 3, 4. 1, 2, 3, 4. Normally we would connect these with an ellipse, but now what we're going to do, since we're dealing with hyperbolas, is we're actually going to connect these with a guide box. So it's a rectangle with those 4 guide points as the midpoints of the 4 sides. Once we get our guide box, what we now do is we now are going to draw the diagonals of that guide box. And what the diagonals of that guide box give us is the asymptotes from our hyperbola. Remember when we worked with hyperbolas before, hyperbolas always have asymptotes. We'll talk more about the asymptotes in just a moment. Now, we have our center. We know it's opening left and right. So the way that we sketch this in, we don't have to use a focal width or anything like that. All we have to do is start on the box, and we're going to go out towards the asymptotes. Make sure it gets closer and closer, but it doesn't touch. Likewise, on this side, we're going to start on the box, and we're going to go out towards the asymptotes. And there is our final graph. Now, just like ellipses, we have some other odds and ends that we need to find as well. So one thing they're going to ask you for is the vertices. The vertices we can read right off the graph. Here's a vertex. Here's a vertex. This one is at 4, negative 3. This one is at 0, negative 3. Now, we also have something akin to the major and minor axes that we had with ellipses. But major and minor imply size. Major is large, minor is small. So the longer one was the major, the shorter one was the minor. The problem is here, we're not really so interested in which one is long and which one is short. What we're interested in is which one runs the direction that the hyperbola opens and which one doesn't. The one that opens the way the hyperbola opens, or runs the way the hyperbola opens, excuse me, is called the transverse axis. And the length of that transverse axis is how far it is from vertex to vertex. Since we went 2 each way, that's a total of 4. The one that runs the way that the hyperbola does not open is called the conjugate axis. The conjugate axis, we went up 4, we went down 4, has a total length then of 8. And so again, sometimes the transverse is longer, sometimes the transverse is shorter. This one it's shorter on. The conjugate is longer on this one. But again, transverse is always the one that runs the direction that the hyperbola opens. It's not about size here. Okay, we need to talk about foci now. Let me make some space here. The foci we're going to do the same way we did with ellipses. And that is we're going to start with the center. The center is at 2, -3. Everything is relative to the center. Don't start from 0, 0 unless the center actually is 0, 0. So start from whatever the center is and leave some space after both of those. The key is that remember that the foci have to be on the inside of the hyperbolas. Right? The curve must curve around its foci, so they must be out here somewhere. They can't be up and down because the curve is not curving around them. So on this particular one, it opens in the x direction. The foci go in the x direction. If it opened up and down, the foci would be in the y direction. So again, it has nothing to do with long or short. It has to do with which way it opens. So the foci are out here. This distance is going to be c, and we need to solve for it. And the way we solve for it is we use the same equation that we used with ellipses except for one change. Remember, with ellipses, this was a plus, and so this was a minus. And I pointed that out in the last video. With hyperbolas, since this is a minus, this ends up being a plus. And so the a squared b squared c squared equation for hyperbolas is actually the Pythagorean theorem. Okay, so now we're going to plug it in. C squared is equal to a squared 4 plus b squared 16, which is 20. So that makes c equal to the square root of 20. Make sure you simplify that to 2 square root of 5. So now we're going to add that to get to one focus and subtract it to get to the other. Since the foci are moving in the x direction, we have to add and subtract that from the x coordinate to get our foci. So we have our center, we have our graph, we have our vertices, we have our transverse and conjugate axes, we have our foci. The only thing left to do is going to be our asymptotes. And the way that the asymptotes work, the two red lines, is relatively easy. And it goes back to what you did in the beginning of the section. I'll make some room up in here. We're just going to work with this particular asymptote. Even though we have two of them, this is the one I'm going to focus on. Notice it goes through the center, which in this case is 2, -3. And it goes through this top right corner point, which is 1, 2, 3, 4, 1. And so all you need to do is you need to find the equation of the line for that asymptote that goes through those 2 points. And so we know that it's going to be y equals mx plus b. We know m is equal to y2 minus y1 over x2 minus x1. That's 4 over 2, which is equal to 2. And so it's going to be y equals 2x plus b. Now I'm going to plug in one of my 2 points. I'm going to choose this one. 1 equals 2 times 4 plus b. So 1 is equal to 8 plus b, which makes b equal to -7. So this asymptote is y is equal to 2x minus 7. Now, for the asymptote, the other asymptote, you'll do the same thing. You're just going to use this point and, let's say, this point. But one thing is really nice about finding the other asymptote, and that is that the other asymptote is going to have the same slope. The only difference is going to be that the slope, instead of being +2, is now going to be -2. So it's y equals -2x plus b. And so now we just have to pick a point, and I would just use the center point. Why not just use 2, -3? You can use any of those that are on that other asymptote, but I'm going to use the 2, -3 this time. And that gives us -3 equals -2 times 2 plus b. That's -4. Add it to the other side, you get b equals 1. So our other asymptote is y equals -2x plus 1. So these are the 2 asymptotes. So this is where those linear equations from the beginning of the chapter come into play. Now, if the center is at 0, 0, this is even easier because if both asymptotes go through 0, 0, that is your b. So you don't have to plug in to find b. All you have to do is find your 2 slopes, which are just opposites of each other. And b will be 0. So it'll just be y equals plus or minus 2x, for example. because b will be 0 on both of them. All right, so that's the graphing part. Now, I mentioned before about a and b. Our a is this distance here. Our b is this distance here. So I did want to point that out again. A is the distance from the center to a vertex. B is the distance from the center to the other end of the box. We don't call that a covertex because the graph doesn't actually touch it. So we do have covertices with ellipses, but we don't have them with hyperbolas. Okay, let's take a look at two other quick examples. The first quick example I want to talk to you about is I want to talk to you about the completing the square. It works the same way as it does with ellipses, but there's one thing that you really have to be careful of, and it's the most common mistake that's made on these problems. And I'm going to point it out to you, and some of you will make it anyway, so it is what it is, but I do need to point it out to you so that you stand a chance of avoiding the mistake. Notice y and x are both being squared. I'm going to group my y's together. I'm going to group my x's together. Notice I'm keeping all the pluses and minuses with them. So that minus on the 25 stays there. I'm going to add 544 to the other side in order to get rid of it. So equals 544. Remember, to complete the square, you must have a 1 in front of the y square, so I have to factor a 9 out. And here, I'm going to have to factor something out as well. I'll do that in just a moment, because that's the part that I want to really talk about, is what's going on over here. So half of negative 6 is negative 3. Square it is 9. But by adding a 9 there, we really made the left side bigger by 81 because of this. So I have to add 81 on this side. Now here, I need a 1x squared. So I need to factor out a negative 25. Just factoring out the 25 will leave me negative 1x squared, which is not correct. I need a positive 1x squared. Here's where people mess up. When I take negative 25 out of negative 25x squared, I get x squared. People are good on that. Problem is, when I take negative 25 out of 200, I get negative 8x, not positive 8x. When you take a negative out of a positive, you're left with a negative, because negative 25 times negative 8 is positive 200. That's where people are going to mess up. And if you mess it up, you're pretty much dead in the water, because your center of your hyperbola will be wrong, which means your graph ends up being wrong, which means your foci and your vertices and your asymptotes, everything ends up being wrong. So be careful with that. All right, so now that we avoided that mistake, half of negative 8 is negative 4, square it is 16, plus 16. Now, putting a plus 16 in there really made this side not bigger, but smaller by 400. So I need to make this side smaller by 400. So I have to subtract 400, because that's really what this plus 16 did to this side. Now I have 9 times y minus 3 squared minus 25 times x minus 4 squared equals, this is 625 minus 400 is 225. And again, like ellipses, this has to be a 1, so I divide everything by 225. Those cancel and give me 25. Those cancel and give me 9. Those cancel and give me 1. And I get y minus 3 squared over 25 minus x minus 4 squared over 9 is equal to 1. And there is our standard conic form of our hyperbola. Its center will be 4, 3, not 3, 4. So be careful with that. And this one will open in the y direction because the y is coming first. So that's how you complete the square. Okay, the last one I want to talk about is one of the reverse engineering ones, and then we'll call it quits. The vertices are at plus or minus 4, 0. The eccentricity is 2. So let's go back to this one for a moment. Sorry, this one. The eccentricity we spoke about with ellipses, eccentricity is still the same equation. It's c over a. But with hyperbolas, the eccentricity ends up being bigger than 1. So on this particular one, our eccentricity ends up being c, 2 rad 5, over a, which I guess I have my a erased. So my a was 2. So that simplifies down to rad 5. which is about 2.2 something. So we're larger than 1 like we expected. So there's our eccentricity. So I want to mention that because we're going to use it on this problem. So the first thing I want to do is I want to organize my information on a graph. Again, that's the key to doing these correctly, is sketching your picture. So the vertices are at 4, 0, negative 4, 0. One nice thing about that is we know that smack dab in the middle of the vertices is the center. And so our center is clearly at 0, 0 here. Also, the vertices have to be in the direction that this thing opens. So it must be going like this. Therefore, that's going to be an x squared minus y squared. So it's going to be x minus h squared over a squared minus y minus k squared over b squared equals 1. But h and k are both 0, so that really just gives us this. Now, we don't know a or b. Sorry, we do know a, excuse me. A is equal to 4. So we know that this is 4 squared, which is 16. We also know that c squared is equal to a squared plus b squared. And so c squared is equal to 16 plus whatever b squared is. Now, we know that eccentricity is c over a. So c over a is equal to 2, which is really 2 over 1. But that does not mean that c is 2 and a is 1. Maybe it means that c is 12 and a is 6. We don't know the original numbers. All we know is eccentricity reduced down to 2 over 1. But the nice thing is that we do know that our a value is equal to 4. So I can plug that in, and now I can cross multiply to find that c is actually equal to 8. Which means this is really 8 squared, which is 64. And so b squared then is equal to 48. I do not need to find b because all I want to do is replace b squared here anyway. So that's 48. And there's my reverse engineered equation. That's it. So those are the examples for today. Have fun with that. Rewind it. Take a look at it if you need to again to make sure that the important parts sink in. And we'll take a look at them in class tomorrow.